Huh? Pardon me? No. It was the window was much smaller, and so I just had to blow it up to be a little bit larger. Okay, everyone. Welcome back. Happy Friday. Hope you're looking forward to the weekend. So here was my thought process, and I wanted to gauge the energy level and stuff of the class, but being right before the weekend and in preparation for an assignment, I really want to get through. I want to get through 3.6, even though we have Monday. Reason being, since it's the weekend, I want to present the material to you, expose it to you, even if it's a little weird, let you struggle with it over the weekend, so that when we have another full day of it on Monday, you'll be able to follow along in the conversation better. The second reason I thought I would throw that on you, even though it might be a lot, is because the first two examples just deal with holes. By first two examples, I mean the order is wrong. Don't pay attention to the actual heading. This is example 3, I believe, on your sheet, and that is example 4 on your sheet. I changed the order from previous years. So that's example 3, and I believe that's example 4. Is that right? Or 5 and 6? Example 5 and example 6. Okay. So, and it's the example 5 and example 6 deal with holes, which I think you've seen before. So I think you can handle it if we do it fairly quickly. Leaving us most of today's class to talk about this thing called an oblique asymptote. Now we're going to talk about the simplest oblique asymptote out there, but that's essentially all you really have to worry about for the majority of this course. Anyways, I don't think you even have to deal with not slant asymptotes until you get to university, okay, unless maybe, yeah, anyways. So I'm going to give you a choice. The whole for this particular function will give us it's going to give us a normal sort of curve like that. Not a big deal. The annoying one, it has a hole, and it will end up with a very atypical shape. It's going to look something like this, and don't shoot the messenger, okay? It's going to look something like that, and it has a hole. Which one would you like to do? The one that you're used to, and you want to try this weird one at home? You want to try that weird one at home, and you do the easier one. Oh, sorry, you do try the weird one now, and you do the easier one at home on your own. What would you like? Option A, do this one, or option B, this one? B. You want to do this one first. Okay. I thought I heard someone say do both. Yeah, preferably. You really? Can you handle that? The information, like just going through disaiming, because you know the test can be annoying. Well, if you're doing it now, it'll be on YouTube for us to look at later. Ah, good thinking. True. I guess it will be on video because I happen to be recording today. Okay, bye. Time for me to do both. Let's do the easy one first then. For those of you who are hoping to do less work today, I am sorry. Me too, actually. I was hoping to do less work. Yes. I am not muted. No, Shay's looking out for me. That's what it is. Okay. It's actually you were. Got it. Well, I appreciate it. Everything's good. Example 5. As a rule of thumb, always factor. Always. Just to see if you're going to deal with an easier graph. And so here we go. Top one is a common factor. So I'm going to make this pen stroke a little smaller. That is 3 bracket x plus 2. And then this would be x minus 4, x plus 2. Just quickly doing a simple trinomial factoring. And lo and behold, yes, we have two factors that happen to be the same. I could divide it. That equals 3 over x minus 4. So as a reminder, graph this. Okay? But remember that there is a hole. What's nice about this one is I don't have to simplify it. The x values are all divided out. There is no x value in the numerator, so I don't have to simplify it and worry about what the horizontal asymptote might be. I already know what it's going to be. So let's leave it. Why do I mention this needless point? It is because when we go to the more complicated version, the more complicated question, the annoying one, I will have to do something about this. So stay tuned. Let's go. The same d. X can be anything, any real number. Obviously, x can't be a positive 4. That is going to be your vertical asymptote. But also remember that x cannot be a negative 2. That's a hole. I highly recommend you give make a little note of what each number represents in the domain so that you don't get tripped up. You don't have to use more brain cells at the end of the question. Because by the end of the question, you'll be tired, right? Let's keep going. Intersect. I always like to plug in 0 first because it's easy. That's a 3 over 0 minus 4. So my y-intercept is 0, negative 3 over 4. Yes?
Somebody mentioned to me that you just need to look at the right side of the equation. You want to shortcut the y-intercept. So you
the right side of the
equation. 3 over negative 4.
Correct. Correct. Something that I sort of discovered while I was trying to explain it to someone before our quiz, yesterday's quiz. If you have ax plus b and then cx plus d, it's really cool. This tells you the vertical asymptote, right? And then this tells you the x-intercept. This tells you horizontal asymptote. And if you plug in a 0, that leaves you with b and d. That tells you the y-intercept. It's pretty interesting. Okay. Do you have to memorize that? Absolutely not. I just sort of realized that was the case while I was explaining to someone. I don't want people memorizing anyways. I want them to be able to use their brains. But I'll leave this here for now if you're copying it, but I'm going to erase it after. Next, f of x is going to equal a 0 when numerator equals a 0. But that will never happen. Therefore, there are no x-intercepts. That 3 will never equal a 0. Let's move on. S for skip, because we rarely ever do it. Asymptotes. The vertical asymptote is 4. And in this question, my horizontal asymptote will be a 0. We'll test it after. Testing. Limit as x goes to a 4 from the left side of the function. Where's my equation again? 3. So this number is going to be slightly less than negative, or just a positive number under negative 4. So it's going to be a positive 3 over a negative small, which is going to be a negative infinity. Limit as x goes to a 4 from the positive side, so a slightly bigger. Oops. That's going to be a positive 3 divided by 4.1 minus 4, a positive small. So I'm going to have a positive infinity. Next, horizontal asymptote. Since the numerator's degree is smaller than the denominator's degree, I know it's going to be y equals 0. Let's test it. Limit as x approaches negative should I change it? Yeah, I'm gonna slightly switch things up today. Instead of putting infinity, I'm actually gonna plug in a very large number. You can still use infinity, but the reason I'm plugging in a very large negative and a very large positive today is because that's what I'm going to do to help explain oblique asymptotes. Okay, so just bear with me. If I have that for f of x, it's going to be 3, so a positive 3 over a very big number, right? A negative big number, or negative infinity. And so that is going to equal very close to a 0. Or how about I just plug in the number? So what is negative 1,000 minus 4? Negative 1,000 minus 4. That's a negative 1,004. That's going to be close to a 0, but just underneath. I'll close that door in a second. Limit as x approaches a positive infinity on the function. So that would be, the 3 is on top, and 1,000 minus 4, that's like 996, right? That's basically equal a 0, but it's slightly above a 0. There it is. And lastly, now that we've done A, the last one is I, the interval chart. And you know, the interval chart sort of confirms your vertical asymptote stuff too, so it's a little redundant at times, but I'm gonna do it anyways. What are we at? My vertical asymptote is 4. My x-intercepts are none, so it's just a 4. 3 doesn't change the value, so it's just x minus 4. So what is my graph? That's my vertical asymptote. Okay, so the graph should be negative until the vertical asymptote and then positive after the vertical asymptote. Let's do it. All of this put together in a graph would be vertical asymptote at 4, and horizontal asymptote at 0. I don't have x-intercepts, but my y-intercept is negative 3 over 4. My vertical asymptote tells me I am very small on the left side and very large on the right side. My end behavior, I am underneath on the left side. I am above on the right side. And if I were to connect the dots with my intervals, I have to be negative and I have to be positive. So don't worry about the highlights. I'm just going to connect the lines here. There. And there it is. One thing that I forgot, don't ever forget, that's like a 0.5 off at least. The whole is still at -2. So If that is x equals 4, my 2 would probably be around here. There's a hole right there. There. Yes?
When you're doing the holes, is it fine if it's colored in, or is it supposed to be like black?
And blank. Okay. Honestly speaking, I really don't want to spend more time doing all the dysamic things more than we have to, because it does take a lot out of you. I would like to get started on the next question, but leave the dysamic analysis for you. Okay? But here's what I would recommend you always start your questions with. As always, please factor. And then I would ask you also to try to divide out your function, divide any x's out of your function so that you can use it for horizontal asymptote analysis. Okay? So if this was a question given to you, immediately factor. Which allows us to deal with a much simpler equation. Okay? But at the same time, you're going to have to do more with this equation later on. So what I'm going to do, also try to demonstrate what you probably will need for horizontal asymptotes. Okay, so as a note, graph this, and this helps for horizontal asymptotes, or how about helps for testing end behavior. So please try.
Does this have a hole?
Yes, because we divided out a factor, there will absolutely be a hole where x cannot equal a 1.
So if we graph the x minus 1 over x minus 2 squared, it would look the same without a hole.
Yes, so if you just graph this, it would be, I believe, if I remember correctly, it's going to look like that. Okay? But because this is where it came from, you have the exact same picture, but you add a hole on it. Okay, so as a note, if you want to, in the corner of your page, if you want to show that it looks something funky like this, you can. The answer to this, all of this is already on our Brightspace. So there, that's it for you too. Okay, just do what you need to. Daniel, are you okay? Hang in there. I feel that way too. Okay, everyone look. Okay, everyone okay? Because I want to spend some time introducing this oblique asymptote. I am totally fine with taking a 5-minute break so that your brain is a little more fresh too. Like, I'm really serious about this. How is everyone feeling? Okay, 1 being I've got 0 in the tank, and 10 being it's my birthday. Like, how do you feel? Okay, that's actually not bad. Okay, okay, we have under 5, we have under 5. Let's take a 5-minute break. Okay, I'm gonna stop the video. When we come back, don't get on your phones because that's not gonna help your brain. All right, literally just take a break, breathe, just sleep, do whatever, and we're gonna go straight into the easier version of oblique asymptotes. All right. Yes. Okay, we are back from our break, and here is us. Am I sharing the right screen? Yes, I believe we are. Okay, so oblique asymptotes. Remember, oblique simply means that it's taking a different shape. So what is horizontal asymptote? What have we done so far? We were essentially testing the end behaviors when we have x equals, for the sake of argument, when x equals negative 1,000, the x equals 1,000, where are we approaching? That was a horizontal asymptote. The oblique asymptote is exactly the same thing, but it's not going to be a line like this. Henceforth, we can't call it horizontal anymore. It's not going to be horizontal. It's going to be, spoiler alert, okay? Your horizontal asymptotes could be like this. Your horizontal asymptotes can now be like this. Your horizontal asymptotes can now be like this. It can now be like this, but not to scare you, we're going to start with slant, aka linear. Okay? Olivia, please don't give me that. I feel bad. I feel bad. Here it is. If I were to say a function was x plus 1, what are some things you know immediately about this function? Hands up. Yes. Whew, you got to go back to grade 9. Come on.
One vertical.
Okay, it's yes. So I'll say this. It has a y-intercept of 1. Remember mx plus b? Okay, it has a y-intercept of 1. What else do you know? Someone else? Yep.
It's a line.
It is a line, not just any line. It is going to be a linear function. And so by linear, remember in grade 9, we talked about slope. Rise over run. Rise over run. And then, rise over run. So I know that this line is going to be something like this. That's a really fat line. Okay. How about that? Okay. All right. What if, let's use our knowledge of holes. What if I gave you f of x is equal to x plus 1, but it's got a multiplication of x and a division of x? What can you tell me about that, considering we just learned about, based on what we just learned? Someone else? Good? Come on. Right. So it's the exact same thing, but x cannot be a 0 because that is a hole. So when x equals 0, I have a hole. It's the exact same arrow, right? It's the exact same arrow, but that is now a hole at x equals 0. Right? So far, so good? So it's the exact same line, right? F of x still equals x plus 1, but now I have a hole. Okay, if you can handle that, what if I gave you, so consider what we did here, right? So this is, let's call this example EGA, this is EGB. What if I gave you this? F of x is equal to x squared plus x over x. Given a rational, what's the first thing I asked you to do in my lesson this morning? Factor it. So if you do, what do you have left? Isn't that the same thing? Right? But here's a difference. I want you to change your mindset a little bit now. We have been dividing by a function. Would you agree? If I am dividing, You have a dividend, a divisor, a quotient, and a, what's the remainder here? Up until now, what was the remainder every time? It was a 0. So I don't have to worry about it. This is something we've done before, and it's very, very nice. But what if I were to, so here's the part where you have to really think. What if I gave you a function that was x squared plus x over x, which is the exact same thing as before, but it's now a trinomial. And I asked you to divide. And since you can't divide this perfectly, it's not factorable, you use your quotient, you use your synthetic. I guess that's a 0, huh? 1, multiply, add, multiply, add, and remainder. What is my result? It would be x plus 1 and a remainder of 1. So you may not know where I'm going with this, but tell me if that makes sense so far. Question?
I don't understand why it's 1 over x for the remainder.
Oh, because I'm writing it in a as a division statement, right? So this would be my quotient, and that would be my remainder, right? So it's a remainder over divisor. Excuse me. Now, you're putting together what we've learned before, but here's the thing. Here's the thing. Okay. So I need you to think about this. On the graph, what would this do? And on the graph, what does that extra little itty bitty thing do? That's the question. And not only for any value of x, but specifically the thing that we talked about before, the end behavior, testing end behavior. I'll give you like a minute. How is this different from the previous? And if it is different, how big of a difference do we have? Yep.
X can't be 0. X can't be 0.
Well, true. I mean, we've been dividing by 0, so there is still going to be the whole. So this is very, very similar to what we had in example B. But the similarity, the difference is this tiny thing. How does that change the previous graph of x plus 1? If you can understand that concept, we're basically done with oblique asymptotes. The idea is this. If the x value is small, like if the x was a 1, that would be 1 plus 1 plus a fraction equaling 1. It changes the number completely, does it not? But before it was 1 plus 1, that was a 2. But because of this, 1 plus 1 plus 1, that's a 3. 2 and 3 are not the same. But let's talk end behavior. When we get way far, not in the center where there's the action, but when we get way far, 1,000. 1,000 plus 1 is? 1,000. 1,000 plus 1 plus 1 over 1,000 is? 1,001.001. 000.
Yes.
0001. No, 001. Okay? Is it that big of a difference? No. In the middle, it makes a big difference. But as we get to the end, we start to see a very similar behavior with the original x plus 1. What I want to talk about, I'll write it down what we just said. If, let's say, how about I write this? So this part, I want it cleaner. This part adds something to x plus 1, right? Therefore, changes x plus 1 near origin. Okay, well, changes x plus 1 by a lot. I guess I don't want to use the not very mathematical term. So I'm going to say, for now, a lot near the origin. And changes x plus 1 by a little far further away. Okay, so I'm going to test it. I will show you. Let's test. As x approaches 1 versus as x approaches 1,000. Let's see the difference. Once again, limit as x approaches 1 for the line x plus 1. What do I get? 1 plus 1, it's going to be 2. But limit as x approaches 1 for the function, it's 1 plus 1, which is a 2, plus 1 over 1, which is 3. That is very different. But if I am testing the limit of an end behavior, so let's do 1,000, for x plus 1, what do we get? 1,001. Limit as x approaches 1,000 for the function, that would be 1,000 plus 1, so 101, or 1,001, plus 1 over 1,000. Which means it is similar. But this is just above y equals x plus 1, right? That similarity is where we can make our declaration saying the quotient is our end behavior. The quotient is our oblique asymptotes. If you see a certain condition, which I'm going to reveal to you, if you see this happening and you divide, what you are going to look for is, what do I get as the quotient? And what do I get as the remainder? It is always going to follow the form of oblique asymptote and whether it's above or below. You might not understand it right now. I'm going to show you as an example. And I'm going to draw all the dotted lines and blah, blah, blah. You're going to suffer. You're going to hate me, but then you love me later. Okay? Everyone ready? Let's see this in action. I understand that I probably took up a lot of space in getting you to write it. I'm going to recommend you try to do this harder one, what do you call it, on a separate piece of paper. Let's ease into it by doing this easier one. Let's use up all the paper space. And I realize now maybe I should have given you a full piece of paper. If you think you need a new piece of paper, you can grab one right now. I'm going to go through all of the samic starting from the top. Please also know that even if you do make it a bit of a mess on this paper, I will have full, neat answer stuff on Brightspace. I'm also going to staple it on the back before today is done, so you can take a look. Any questions? All right, let's get started. First off, just in case I might have a hole, let's factor. This is x minus 7 with a x plus 1 all over x plus 5. No holes. Okay, so should I divide out, right? Just because it helps us with testing for oblique asymptotes. I mean, testing us for horizontal asymptotes. In this case, what do you notice about the degrees? The numerator.
Is greater than the denominator.
If you look at our characteristic summary sheet from the previous class, you will see that if the denominator's degree is larger, you immediately have an oblique asymptote and you have no horizontal asymptote. Horizontal is gone. So before we do any of the dysamic, let's do the annoying part, which is the division. I am going to do synthetic. -5. We've got 1 down, multiply. Add, multiply, and then add. There it is. That means f of x, if I were to divide the x plus 5, I get myself 1x minus 11 plus 48 over x plus 5. And based on my previous example, trying to introduce oblique asymptote, what does this mean? It means this is my end behavior. At the end of the day, my graph is going to look like that. And what is that? This portion will tell me if you are above that line or if you are below that line when you're testing end behavior. Because you're adding a little something to it. It's going to either push it above or push it below that line. Okay? Now, using this, from this point on, there's nothing really different. We are going to do dysamic until we get to the oblique asymptote, where I'll show you how we can test it. So go ahead. If you want to wait for me, you can. But if you want to try it yourself with dysamic because you think you can, you're that comfortable, go for it. XCR, X cannot be -5, and that's a vertical asymptote. It is not a hole. Intersect. If I plug in a 0, I would get a -7 over a 5. So my y-intercept is 0 and -7 over 5, or 1.4, your choice. Yep.
Why are you using that equation instead of the one you found? Like that, -11.
I could,
Would it give you the same answer?
of course. You can try it. So I'm doing whatever's easier for me. If I stick a 0 here, that becomes a 0, that becomes a 0, that becomes a 0. I've got this left. It's just easier. Next, f of x will equal 0 when numerator equals 0, which means I factored it already. That means x will either be a 7 or a -1 for my x-intercepts. So x equals 7 or -1. I have 7, 0 or -1, 0 as my x-intercepts. Let's write that down so that I don't have to search for it later on. S for dysamic, I'm going to skip as usual. For asymptotes, I will quickly test vertical. -5 from the left side for the function will give me, let's see, a negative times a negative divided by a tiny, tiny, tiny negative. That's going to be negative infinity. Limit as x goes to -5 from the positive side. That's a negative times a negative divided by a tiny, tiny, tiny positive. So it's going to be positive infinity. I don't have to worry about HA. I'm going to move on to oblique asymptote. What is my end behavior based on my division? You already did the work. This is why I asked you to do the division first. My end behavior will be x minus 11. But is it going to be above or below? Take a look at how I test it. If I were to test not the function, and I were to do x minus 11 on its own, what's my answer? -1000 minus 11. I have that. And limit. If I were to test way to the right, and I have x minus 11, what will my answer be? Well, 1000 minus 11, it'll be 998. Oops, 989. Compare that with, if I test the limit for the function, right? Which is x minus 11 plus 48 over x plus 5. As a reminder. Well, -1000 minus 11 is going to be -1011 plus 48 divided by -1000 plus 5. That's going to be -995. So, based on this, is this going to be above -1011 or below? It's going to be less than -1011. Therefore, if I go to the left, it will be under the y equals x minus 11 line. I'll do it one more time. So that was the left side. For the right side, I have positive 1000 for the function, which is x minus 11 plus 48 over x plus 5. If I have 1000 minus 11, I will have 989 plus 48 over 1005. Is that going to be bigger than 989 or smaller? It'll be bigger. So it's going to be less than, greater than. Therefore, if I go towards the right, this will be over the y equals x minus 11 line. For the sake of your brain activity, I'm going to skip intervals, but you can definitely do that too to confirm your graph. Let's draw it. I don't have any space. I recommend, if you're sketching this, please have a slightly larger space on the bottom of the graph. And the reason why I recommend that is because my straight line has a y-intercept of -11. Here we go. Ooh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 11. Which means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, pretty close. It's a dotted line. Okay. This is my y equals x minus 11 line. And my vertical asymptote is -5. -1, 2, 3, 4, 5. At this point, some people might be asking me a question about how to draw this oblique or how I did it so quickly. Anyone have issues with that or any strategies you want me to explain? In case you're a little embarrassed or you're a little shy about asking, let me try to explain what I do. As always, I start with the y-intercept. That tells me where my sketch should begin. From there, I literally just count the slope. 1, 1, rise, run, rise, run, rise, run. And if I do that, because the ratio is 1 to 1, my x-intercept here is going to be 11 as well. -11 and +11. And I just stick a line there. I don't do anything particularly special. And there is my vertical asymptote of x equals -5. So I have completed this. I have completed this oblique asymptote. Okay. I also need to plug in y-intercept, which is -1.4 right here. I need to do my x-intercepts, which is 7 and -1. 1, 2, 3, 4, 5, 6, 7. I have to do my end behavior. Left of the vertical, I'm down. Right of the vertical, I'm up. Left of the vertical, I am down. Right of the vertical, I am up. It's just not staying right there. And then left, so end behavior, left side, I am under the oblique asymptote, which is right here. Oops, oops. And to the right of, on the right side of my graph, I am going to be above or over the oblique asymptote. That's all we have. The chart will also show you some more information, but I'm skipping the chart just to demonstrate. From here, I somehow have to go back down, teleport up here, touch these 3 dots, and end up above that dotted line, because that's my end behavior. So we have, try to have a thicker line. That. Oof, that wasn't a very good line. Let me see if I can do it again. Oh, wow, that's really bad. Okay, not bad, better. oblique asymptotes. How is this any different from what you've been doing? If you take a look at the analysis, there's nothing different, but you have to keep an eye out to see what the degrees are. You will end up having to do an actual proper division if you know that it's an oblique asymptote. Why? Because it reveals so much information for you. You could think about that as a step and memorize it, but if you don't do that, that's okay, because it will, when you get to the testing portion, you realize you have to do it anyway. So even if you forget this step, the same will remind you that you have to do it. Okay? And then you figure out that. Right now it's new, so it's gonna hurt you a little bit and you'll feel a little bit confused. I want you to have this and try at home. So your homework essentially is come tempered, okay? Come beaten around with math a little bit, but with a little bit more exposure to the dysamic portion for obliques. Try the slightly annoying one. I gave you the clue of what that looks like. If you have it in you, I'm gonna actually say, don't do, should you do? Let me see which one is more manageable, because this is the first time you're doing it by yourself. You know what? Yeah. I'm gonna ask you to try example 7, as well as practice 1 and practice 5 to start. And please note for this one, before, in case you make a mistake and you get really, really frustrated and give yourself a really, really bad start to this, please note that for this function, it's missing an x term. So if you're doing a division, please remember to stay true to your divisions. There is a 0x there, okay? Please try example 7, practice 1, and practice 5 before you attempt anything else for oblique. Okay? Holes can be mixed in, so please be careful, always factor. If you can do those and you want more to test your metal, 3 and 4 is a good place to continue. Number 2 is just flat out rude. So if you really want to challenge, try 2, but you know where I'm going with that, okay? Your package, does it also have more oblique practice at the very back? You could try that as well. However, you could try that as well. I don't have a full answer key to it yet. I've done the first 3, but as you can imagine, it takes a little bit of time for me to make an answer key. So stay tuned, expect something for that maybe by Saturday or maybe by Monday, depending on when I get around to it. There it is, oblique asymptotes. Your asymptotes are no longer horizontal. They can take positive or negative slope straight lines now.
That's it. The degree on top is greater than the
Correct. Degree on top. I made a little note here. You see that, you know, it could be a linear asymptote, it could be a quadratic or even a cubic or whatever. You're not worried about that stuff. Yes, they exist, but I want you to focus on learning how to do that first. I don't think so. I don't think we'll have time. Remember, oblique is not even in the textbook. 3.6 is something that we as Northerners have created. So there are some students in other schools that won't do oblique because the teacher's lazy. Because it's not in the textbook. So some people are going to university not knowing that obliques exist. Okay, do your best. All right? Okay. Let's close that video.